Welcome back to my Back to Calculus channel. In this lecture, I will discuss a triple integral where we want to integrate y inside the domain V. V is bounded by x equal to 4 minus y square minus z square and x equals y square plus 3z square. So we have two surfaces, and the portion of the volume bounded by those two surfaces in the first octet. So the first step to solve this integral is to identify the limits or identify the boundary. We can easily see that inside the volume V, we have x less than this surface and x less than the other surface. So this can be easily identified because x equal to 4 minus y square minus z square is a paraboloid opening to the left. It's a paraboloid opening to the left. When you can see that when y equals 0 and z equals 0, x equals 4. And x cannot be greater than 4. So x has to be less than 4. Because if you put x equal to 5, then 5 minus 4, which is 1 equal to minus y square minus z square, which cannot be solved. The second surface x equals y square plus 3z square. It is a paraboloid, but it is an elliptic paraboloid because y square plus 3z square is not a circular cross section, and it is opening to the right. So this surface is opening to the right, so x should be greater than or equal to this expression, and this surface is opening to the left, so x is less than or equal to 4 minus y square minus z square. So this is something, the first step we need to figure out to solve a triple integral. We need to identify a boundary of the volume with respect to one of the three coordinates. Here we have found that we can set the integral x from y square plus 3z square, y square plus 3z square. We can integrate from this to 4 minus y square minus z square, and we can integrate this function y with respect to x, and then we will be solving iteratively other part of the integral. For now, we don't know the boundary of the other two variables, so we split the integral into a double integral which is outside and a single integral which is inside. So that means we are going to write the integral like that. So the triple integral y dp is a double integral with respect to a domain D and a single integral or line integral, and this integral inside has to be solved first, and then you have to figure out how do I solve the double integral. And this inside integral is easy because we are integrating y with respect to x, so y remains constant, and the integration will be just 1 dx, which is x, and the limit is y square plus 3z square 4 minus y square minus z square dx. Okay, so all we now care about the inside integral, and let's simplify that. expression. So we can set the upper limit of the function, the variable x, which is 4 minus y square minus z square, minus the lower limit, which is y square minus 3 z square, and just to carry forward the double integral. And maybe at this stage we simplify that further. So we can see that this is 4y minus 2y cubed minus 4y z square, y times z square dx. Now it is time to evaluate this double integral, and we have to figure out the limit. So let's first take a look at what is that condition on the surface. So we can see that if I look at both surfaces, 4 minus y square minus z square equals x, and x equals y square plus 3z square. So from that we get 4 equals, if I take y square minus y square and z square to the right hand side, so I get 2 y square plus 4 z square. Now we can divide by 2. So y square plus 2 z square, and this is a ellipse. It hits y axis. So if you set z equal to 0, you get y equals plus or minus square root of 2, and if you set y equals 0, you get z equals plus or minus 1. So this is an ellipse, something like that. So set your y axis, z axis, and leave your x axis here. So we can just use the right hand rule to set the coordinate ordering, which one is x and which one is y. We are not worried about x at this stage because we have already integrated with respect to x. Now the other condition, we know, we are given that the volume is inside the first octant. So in yz plane, the first octant would be this one. So the first octant is y positive, x positive, z positive. Okay. So that tells me something. If we look at from this ellipse, we can go it two ways. So let's say if we try to solve for y. So y square equals 2 minus 2 z square. So y equals plus or minus square root of 2 minus 2 z square. Okay, so y equals square root of 2 minus 2 z square. One is this upper part of the ellipse. So maybe let's identify that in the first attempt. So the upper part is this one in the first octant. We restrict it to the first octant. So that means we are going from z from this line to that line, and y from here. So let's identify that the other way from this part. Okay, so what we can see here is that we can just evaluate this double integral. The y limit will be from 0 to square root of 2 minus 2 z square, and z limit will be from 0 to 1. We can integrate that 4y minus 3y cube minus 4y z square with respect to y, and then with respect to z. And this is just an iterated integral. You have to be careful, since you have one of the limit is dependent on the other coordinates, so iterated integral has to be done one at a time. So let's first solve this inner integral. Integrate 4y minus 3y cube minus 4y z square with respect to y. So I get 2y square minus 3 over 4y4 and minus that remains constant when I integrate with respect to y, so that should be 2y square z square, and the limit going from 0 to square root of 2 minus 2z square. Carry forward the integration with respect to z as is. So we are now working for the integration with respect to y, which is this inner integration. Okay, so all we have to do is substitute the limit. Where I see y, I put the upper limit square root of 2 minus 2y square. So here I have y square, so square root cancels. I have this minus 3 over 4 y to the power 4. So y to the power 4 is y square to the power 2. So y square is 2 minus 2z square, because this is y. When you take y square, square root cancels, and then in order to get y to the power 4, you square it again. Okay, and 2y square z square, that's easy. 2 times 2 minus 2z square times z square, and we have we have to integrate that with respect to that. It will be a good idea to simplify that. We can multiply and collect terms. We can first square this part, simplify this part, multiply by z square. That's not difficult to see that it is 2 minus 4 z square plus 2z4. If you can't work it out using mental math, I square that. 2 square is 4. 4 by 2 is 2. So that will be a negative 2. 4 minus 2 is 2, and so on. So you can have this expression. Okay, so now this is a simple line integral that we can solve. 2z minus 4 over 3z cube plus 2 over 5 z to the power 5, and evaluate it from 0 to 1. And that is set z equal to 1 such that if I add them together, 16 over 15. Okay, so this example sets a nice criteria to understand how do we solve triple integral. And this is an example that I like the best, is because this helps completely understanding how do we solve triple integral. Let's recap. So to solve a triple integral, our strategy is, one of our good strategy is to split the domain in a way that identify a line integral that is easy to solve. So in this case, we have found a line integral that is easy to solve. So we solve this one first, and then we solve a double integral, because the total integral is a triple integral.